Right, now let's apply diversity to this demand that we've been talking about. So installation outline. First step in preparing an installation design is to identify the electrical loads. You're going to approach the client and you're going to say, what do you want? And they're going to say, I want this, and I want this, and I want this. And the domestic, this is where, they're going, oh, we want this, it's like 10 kilowatt hob or this induction hob, and we want this, and we want this. And you'll be looking at their supply and you'll be going, But commercially, it's where you're going to have to get a realistic understanding of what they want. You're then laying it down and you're going to assess the demands and apply diversity to those. Okay, you're going to look at the physical position of the loads required, as well as the kVA demand, power factor, that's important as well, voltage, frequency, etc. Okay, we can then draw this down, position of the main incoming board, main sub-mains, distribution assemblies, and you can actually do this for your project before you even start going onto the actual wiring diagram or the drawings that they send you. You can actually do a installation outline drawing, sub-mains, DB1, DB2, DB3. You may have, obviously, in your project, you may have an office space, you may have a workshop space, so you may want to dedicate a DB for each of those spaces. You may have an area of significantly high demand, so you may have a dedicated DB to that position, but you can put it all down onto a installation outline. It's very, very useful. The basic intent is to use standard final circuits wherever possible to avoid repeated design, providing earth fault loop impedances are kept below the respective maximums of 0.35 and 0.8. This is an illustration of an installation outline, just a little example here. So you have your incoming supply, your metering, and then you have your total IB, your total design current, which is a combination of the three sub-distributions. There's sub-distribution A, sub-distribution B, and C. So these are sub-mains, and then here's your final distribution points. Just a simple sample. Final circuit demand. The current demand of the final circuit is estimated by adding the current demands of all points of utilization. Add them up. And then you take any equipment connected to them, you add them up, but you make allowances for diversity, as we've said. The following tables give current demands on the use of final circuits. Now, I've taken these straight off from the on-site guide. The on-site guide has been the same for a while. The design guide, I'm using the design guide's examples here, the electrician's design guide. Now, the examples they give in the design guide aren't really correct, and I'll explain why as we come to those. But just for you to follow it if you have them at hand, I'm just going to copy them straight away out of this book. So this is the first table you'll see in Appendix A, or if you have the previous Amendment 3 version, it'll be Appendix 1, I think. Okay, so the current demand to be assumed for points of utilization and currents using equipment. You hopefully have used this before. So we have any socket outlet other than 2 amp and other than 13 amps. So it's a 5 amp, a 16 amp, a 32 amp. It's rated current. That's it. Yeah. So we don't. At the end of the day, if you have a 16 amp lead for something, it's probably more than 13 amp. So we just use the rated current of the demand there, of the equipment. For 2 amp socket outlets, at least half an amp. Lighting outlets, this is important. The current equivalent to the connected load. So the wattages, you add the wattages together. You may have to have some factors applied due to the lagging and the leading of the control gear, unless the manufacturer has specified as such. If you're just putting up ceiling roses, pendant sets, baton holders, although we can't buy them now, you can still obviously obtain 100 watt lamp holders. So we're still using them as the assumed potential maximum demand for every single lamp holder. So minimum power of 100 watt per lamp holder, unless you know the power of the lamp. So again, if you're designing it and you're providing them with a load of 4 watt low energy lamp holders, that's fine as long as they don't replace them for 100 watt ones. Electric clock shaver supplies can be neglected, they're of negligible demand. Household cooking appliances is the one that they like to play with. And do remember, it's the household cooking appliance. It's very important to remember the household word there. This only applies if it's a domestic cooker. So we'll take the first 10 amp of the total rated current plus 30% of any remaining. Okay, we'll put this into an example in a minute. And if you have a control panel with a socket outlet, you may use a kettle in there or a toaster or something. Just add 5 amp onto it. Why not? Any other stationary equipment, we just take the standard current or normal current for that. So here's a little example, a shower circuit. Yeah, it's taken out the design guide again. So I'm keeping it at 240 volts because it's in the design guide. And remember, if a shower says it's 7.2 kilowatt on the label at 240 volt, you don't use 230 volt to calculate its current. You stick to 240 volt because that's the value of the voltage that dictates the power. But look at what the manufacturer's stated voltage and power is. Okay, so power over volts, or UO times cosine over 1000. Cosine is applied for power factor. Yeah, so don't need that. The over 1000 is for the wattage. So current 1000 times 7.2, so 7.2 kilowatt. Yeah. Over 240 times 1, because there's no power factor, is 30 amp. 7.2 kilowatt, 240 volts. It's 30 amp. Okay, so that's a shower. Should be a piece of cake, that. Cooker. Consider an electric cooker with 4 3 kilowatt hobs on the top, a 2 kilowatt main oven, a 2 kilowatt grill. Now, the total installed capacity is 16 kilowatt. As an example, 1.1. So we've just calculated it as power over voltage. No power factor. It's not a motor or anything like that. We've got 66 amp then. But assuming this is a domestic or a household, we can apply the diversity of 10 amp and 30% of the remainder. So what we do is you take 10 amp away from that, so that's going to become 56. You multiply 56 by 0.3 or 30%, then you add the 10 back. Oh, that's how it's written in the book. The way it's written in the book is a bit confusing, but it's the 10 plus 30%, 30 over 100, of the remainder, which is 66 minus 10. Yeah, so it's 30% times 56. Don't know why they have to write it that way, but that's just the way it's in the book, so I've written it there. Hence 30 or 32 amp will be selected for a potentially 66 amp cooker. Now remember, this is assuming a household. If you had a cooker being used in a canteen or in a coffee shop or something, it's probably going to be under a much larger substantial load, and you probably wouldn't apply that diversity to it. Third example is a light circuit. Consider 10 downstairs lights, assuming 100 watt per light point, so that's 10 times 100. Okay. Over 240, 4.16. A 5 amp will be fine. However, if this is one kitchen, and these are 10 lights in one kitchen, and you turn them on one single switch, 10 lights switching in, maybe a significant rush current, maybe, to trip if it's a sensitive type B circuit breaker. So you may want to jump that up to a 10 amp. If, however, that is 10 lights in 10 rooms on one switch, then no. This is the difference with demand diversity as well. You've got to consider the energizing of the equipment. If it's all at one time in the inrush, you may have to consider changing your protected device. 1.4 immersion heater, 3 kilowatt. That's just 3000 over 240 is 12.5 amp. There's no problem with that one. Motor has a power factor of 0.8 due to the lack of the back EMF. So we now are going to use this cosine theta. Okay, so 1000 times 3, which is 3000, over 240 volts times power factor to adjust the voltage to tolerate the back EMF equals 15.6 amp. Okay, we're going to cover power factor with some of our equipment in our design later on, but do remember when you do your project, if there is a need to apply power factor, it will be given with the specification. Okay, if it's not given with the specification, then just make sure that the manufacturing data that you provide, if there's a power factor stated on it, then you apply it to your design. Alright, so diversity between final circuits for simple installations. The allowances for diversity are for very specific situations and can only provide guidance. The figures given in the table may need to be increased or decreased depending on the particular circumstance. Diversity, the problem with diversity is it changes according to the scenario, and this is, as I say, guidance. Your key point in question would be your project, which is a test centre for 2017-18. That's a type of system or a type of building that is not similar to any of these, so your diversity will be different to these requirements, because you'll be thinking, well, a lot of these circuits are actually not going to be used for demand, they're going to be used for access to a source of supply. The current demand of a group of final circuits supplied from one distribution board and submain may be estimated using the allowances for diversity given in table A2, which I'm about to show you. The allowances of rows 1 to 5 are applied to the current demand of the equipment supplied by the sub-distribution board, each piece of equipment. Row 9, however, applies to the rated current of the overprotected device for the circuit, and row 9 applies to socket outlets in a household type scenario according to Appendix H, which basically means your A1, A2 or A3 ring or radial final circuit. And that is where the design guide is a little wrong with the way it uses those. So this is the table. The key things to note, first of all, here's the purpose. Lighting, heating, cooking, motors, water heaters, thermostatic. Fine, great. This one here is for your household type ring or radial according to Appendix H. This is a column for your household. This is a column for your small shops, stores, offices and business premise. And here's your small hotel boarding, etc. Okay, so we'll go to our first example then. Small office. So if we look here, small office, we're looking at this column here. So we've got 20 times 100 watt fluorescent luminaires. Now with fluorescent luminaires, we also have to take into account the 1.8 factor, which you'll see in the books, which explains the control gear issue, unless the manufacturer's given us another value. We'll see that in a minute. But first, let's see. It says here for lighting, it's 90% of the total. So for lighting, 20 of 100, 20 of 100, it's 90% of 20 times 100. And there's that factor of 1.8 over the 240. Okay, 13.5 is your total for the light one. Let's put the light one aside. Next one is power. Now power was heating and power, 100% of the largest, 75% of the remaining. So 100% is 100 over 100 of 10 kilowatt over 230 is 43.4, and 2 kilowatt is 75% of 2 kilowatt over 230 is 6.52. Alright, I mean, if you're confused with how to do this, just do this 10,000 over 230 times 1 and 2,000 over 230 times 0.75. That's the easiest way to calculate them if you find it harder. Okay, so therefore we're adding these together, and the power demand is, or the power with diversity applied, is 49.92. Great. The third one was two 32 amp sockets installed. I believe it was A1 Appendix H. If you look at A1 Appendix H, it says 100% current demand of the largest and 50% current demand of every other circuit. Now, what the design guide would do with these every other circuits is it would apply that to all circuits. That's wrong. It's all other circuits that are of this type of circuit. This is demand for these types of circuits. This is the demand for these types of circuits. So how many other circuits are there? There's one. There's two in total. So we'll take 100% of one and half of the other. So that's 100% of 32 and half of 32. 32 and 16 is 48. So we're going to add these three circuits together. 13.5, 49.92 and 48. This gives us, for the small office, a maximum demand with some diversity applied of 111.42. That's from the tables in the book. You can then decide if that's suitable to what you're looking at. If it's not, then scratch your head and decide why the installation isn't going to be used the way the table says it will be used. Okay, let's go another example then. Okay, so for the domestic installation, we're going to consider the previous examples for the cooker. That was where diversity brought it down to 26 amp. The shower, which was just 30 amp, no diversity applied. We'll do light circuits from example 1.3, which is I think 4.65 amp each, and two simple 32 amp socket circuits. Now the diversity for the domestic is such that we can apply 66% of the total current demand for the lighting. We apply 40% to the second largest socket outlet circuit. There'll be no diversity for any water heaters that are thermostatically controlled, or the largest instantaneous, so that's the shower, and the cooker is the household, so we know that'll be 26 odd, so that's fine. That'll be like we did before. So we're going to have 26.8 for the cooker, 30 for the shower, two circuits at 4.16 for the lights, but we'll apply the 66% to them to bring those two down to 5.49. 30 amp for the first socket circuit, 40% of the second. That gives a total maximum demand with applied diversity of 104.29 amp for the domestic installation. Now, immediately you're like, well, that's just stupid, because, you know, that's too much. But you need to question what you're looking at here. We have an installation demand of 104.29, but, you know, 26.8, 30 amp, you know, 56 amp of that, you know, 56 amp, more than half of the installation's demand is the cooker and the shower. Now, question one, are the cooker and the shower going to be used at the same exact time? Now, in a very, very, very busy house, maybe a slim chance, you know, but again, the conductors have got to be under this considerable load for more than half an hour to then start to become thermally affected. So it's obviously not going to be this much. So what I would do is I would apply some further diversity to this. It's as long as I get a good understanding that the cooker and the shower are going to be used for, you know, short duration now and then, a couple of times a day, and most likely not at the same time, I'm not under any concern with this demand. This is a good example of how the maximum demand and diversity kind of gets ignored, because when you work it out to the guidance, it doesn't work for you. You've got to kind of then take further engineering judgment and common sense to it. Okay? Alright. We're going to do one more example. But what I'm going to do is I'm going to leave it up, and when I come back on the next video, we'll do a solution. So, you know, I could sit here and let you look at it, but you might as well just pause it or something. But here is another example of one that we will do. Light circuit 1 with 20 times 58 watt fluorescent luminaires. Don't forget the 1.8 factor for the fluorescent luminaires. Light circuit 2, 8 times pendant sets and 2 500 watt PRR floods. Now remember, the pendant sets are just 100 watts because, you know, you have to assume they can go into that. We have a cooking circuit, appliance 1, appliance 2 and appliance 3. Okay, so they're cooking appliances. It's not a combined cooker, they're just heating equipment, cooking equipment. 3 power appliances, 4 socket circuits of the 20 amp type, 4mm radial. Have a play with it, see what you come up with, then I'll do one, and if we're somewhere like within 20 amp with each other, we'll probably be fine. Okay, good luck with that, and I'll see you when I put the solution up in a couple of days. Cheers.